Okay, so in this part, we want to return to talk about sinusoids. We just talked about using the one-link planar robot and trying to plot that out and seeing what it might look like. And here we want to talk about it. So the general form of a sinusoid is of the form y of t is a times the sine of omega times t plus phi. So lots of Greek symbols in there, lots of weird things that we may not be comfortable with. We talked about this at the beginning of the semester. Just things we kind of have to deal with. And so what do these things mean? So we talked about it a little bit in the video. We've got basically 6 different variables we have to worry about with the sinusoid. One is the amplitude. That's A. And that is the max absolute value. Or I should say absolute deviation. Because it may be, as we move forward, that we use some sort of shift and the wave is starting, instead of starting at 0, it starts up higher. And so it may not always be centered across the axis, but it's how much it fluctuates. So from the center line. So for our one-link robot, I'll just kind of keep up these as we go. So for our one-link video, if you want to go back and refer to that one, our amplitude was equal to L, was equal to the length of the robot, because the max that our Y or our X varied was at a length of L or negative L. The second thing we come across is this omega. And that's the angular frequency. And that is basically how many radians per second. That's our rotation in radians per second. And again, that makes sense. If we remember back from dimensional analysis, I guess things we took for granted here is that, t is time, and y is kind of position. Y, or we could have used x. Both of them had that thing. We used y because we call them sinusoids, even though cosine is just a different form of that. So it's our rotation in degrees. And then 3 is our phase angle. Phi, which is where rotation begins. So for our one-link robot example, our angular frequency was basically 1 radian per second. Remember, we set it to where it was, it took 2 pi seconds to go 2 pi radians, so that was 1 radian per second. And we set that our phase angle started out at 0. Now, there's some other things they talk about with regards to these that kind of play into the other parts. You might hear the phrase frequency. Which we use an F for that. And it's usually measured in hertz. And if you don't know, a hertz is 1 over a second. And basically the way we get at that is that omega is 2 pi times the frequency. Or the other way to think of that is frequency is omega divided by 2 pi. So essentially it's how quickly the angle changes with regards to radius. And I mentioned on the previous video so just a couple ways to look at that. Either way, you get frequency. Number 5 is the period. And we use capital T for that. And that, as I said, was how long it takes to repeat. So again, that's generally measured in seconds. That's measured in hertz. We talked about this, measured in radians per second. The phase angle will be measured in radians because it would have to be the same units that are in there. Yeah, but how long does it take to repeat? And so that is just a matter of T is 1 over the frequency. So frequency is essentially how many times it can go through, how many rotations it makes in 1 second. And so the period is how long it takes to actually make one. So we mentioned before that the frequency, or the period for this one, was 2 pi seconds. And I didn't say it back here, but the frequency for this one would of course be the 1 radian per second divided by 2 pi. So it would be 1 over 2 pi hertz with the frequency for our 1 link that we talked about previously. And the 6th thing we talk about with regards to that is the phase shift. And this doesn't really have its own variable, but it's measured in second. A lot of times I'll just abbreviate it as PS, for lack of a better term. And it's equal to our phase angle divided by our angular frequency. And therefore, you can tell that it's measured in seconds because frequency is going to be measured in radians. We're going to divide it by radians per second, so we'll end up with seconds back on top. And so in this case, our phase shift, since our phase angle was not off, it's also going to be 0. So essentially, it is how much of a rotation are you off? Not how much of a rotation. How much? Yeah. How much? Not of a rotation. How much time? Are you shifted? So our phase angle tells us that instead of starting at 0, we started at some angle. This phase shift translates that back to, okay, moving at our constant rate omega. How much time would it take to be that? So what time constraint are we on for that? So it's measured in seconds. And those are essentially the 6 factors that we need to know about sinusoids to be able to work them out later.